what we're looking at here is I'm looking at the Chapter 5, Notes 03, and we're just going to kind of run through this together. The idea in Section 5.3, we're skipping Section 5.2 FYI, in case you haven't figured that out. And you'll notice on the problem set, we went 1 through 14, and then we're going 47 to 62, right? So don't do the problems in between there. Anyways, so what we're doing in this section 5.3 is called proving identities. And I know that when we say the P word in mathematics, a lot of us get a little freaked out. But there's nothing to get freaked out about, as these proofs are not like geometric proofs. They're like an algebraic proof, and it's just basically like doing one of these simplifying problems that we had done in Section 1, except you're told what the answer should be. So it's basically just kind of using your identities or algebra to make one side look like the other side. So I'm going to start by outlining kind of 3 general strategies that we can use to do these sorts of problems. These are only suggestions, so they're not like you have to do one of these 3 things, or you might kind of do something in a combination or something kind of a little bit different if you see something clever, but this is just, in general, these are useful things. So we're going to start with one side of the equation. It doesn't matter which one. Now, there'll often be the case where you can make your life easier by choosing one versus the other, but it's always possible to go either way, choose either side. And we'll talk about, as we get into some of these examples, how you might choose which side to work on, one versus the other. Okay? So that your proof ends when both sides of the equation are the same. Okay? And the steps in between are your proof. So these problems are purely based on the work you've shown, because you know the 2 sides are equal. You know the one side is going to turn into the other side. What I'm going to be grading is how you're showing me to do that. Okay? So you really need to think about this as like a performance or a demonstration. So you need to make sure you're being organized and being clear and writing neatly and not doing too much at one time, right? This you should be thinking of, okay, if I was going to explain this to a classmate, how I go from here to here, I don't want to skip a lot of details. I want to make sure I include enough details so that if somebody that kind of knew what was going on could follow what I'm doing. Okay with that plan? So we're going to start with one that's a non-trigonometric proof. to kind of get our feet wet. So here we have x squared minus 1 over x minus 1 minus x squared minus 1 over x plus 1 is equal to 2. So again, we're going to pick one of the sides to work on and try to make it equal the other side. Which side do you think would be the better one to work on here?
Probably the left is positive.
Yeah, in general, it's typically going to be easier to go from something that's more complicated to something less complicated, because you do like reduce and combine like terms, and the kind of algebra that we're going in the kind of direction algebraically that we're most comfortable with. It's typically more difficult to go from something simple to something complicated, unless there's an obvious thing to do, right? With the number 2, there's nothing obvious I can do with that to like break it apart and make it really more and more and more complicated, right? So that would be why I would probably start with the left side here. Does that make sense to you guys? Okay. So we're going to start with the left side. So we have these two rational expressions that are being subtracted to one another, or from one another. There's a couple of options that we can do here algebraically. What are some things that we can do here?
Common denominator.
Okay, we have two fractions that are being subtracted, so we could make a common denominator and do the subtraction. That's one thing we could do. Great, what else? Okay, so what would factoring the tops allow us to do? Potentially?
Cancel out.
We could potentially reduce these two fractions, right? They're two fractions. There's possible I could reduce those. Great. Everybody okay with that idea? The third thing that I think we would struggle to come up with is, you'd notice there's a greatest common factor here, that you could factor that off. That's probably not going to be helpful in this. But of those three options, which one do you think is going to be the best one to start with? Reducing. Yeah. So they're all going to be okay. Any one of those you can still use to get to the correct answer. It's a question of like, how messy is this got to get along the way? Reducing, as you might suspect, is going to help get this thing smaller quicker, right? So Rami suggested to factor the numerators to allow us to reduce. If you look at those numerators, does anybody remember how we factor something like that?
X plus 1, x minus 1.
Great. Those are a difference of two squares, because you have something squared minus something squared. So you have like the square root of x squared plus the square root of 1, and then the square root of x squared minus the square root of 1. Does that ring a bell? You did it last year, and it's been a minute. Yep. So we got it all factored. Any questions about how we did that factoring? Okay. To reduce these, do we see anything that can reduce?
Yes.
Yes. What can reduce?
X plus 1, x plus 1 in the numerator denominator.
Okay, so in the second fraction, we have an x plus 1 in the numerator and x plus 1 in the denominator. Those can reduce out.
X minus 1 over x minus 1.
In the first fraction, we can reduce the x minus 1s. Everybody's okay with that? Remember, when we cross these out, what do they become? Ones, right? So really, we have 1 times x plus 1 over 1. But really, that's just x plus 1. We're okay there? And then we have 1 times x minus 1 over 1. So really, we have x minus 1 there, right? But this is not quite correct. I've made a mistake in writing this down. This is a mistake that I think that almost every single one of us would make. Does anybody see the mistake here now that I'm alerting us that there is a mistake?
It's probably wrong. Are they both supposed to be positive?
No? Ariana? Yeah, where is there a missing set of parentheses?
Around the x plus 1 and then around x minus 1.
Yeah. So the parenthesis around the x plus 1 doesn't really matter, right? Because there's no positive or there's no negative sign in front of it. So that part doesn't really matter. But the negative sign around the x minus 1 absolutely matters. Because we have a negative sign in front of that, we need to make sure we distribute that negative through. Does that ring a bell to everybody? Now that's one of those that's easy to miss. Doing okay? Now what should we do? Jay? Good. Yeah. I have a positive x and a negative x. Those cancel out. And 1 plus 1 is just 2. And if you remember, what are we supposed to equal? 2. So we're done. That little box at the end is just your period to indicate your proof is finished. Jay?
Why do the ones matter? Just like, you wrote it the same way that you wrote it. Why do you need to write the ones there?
So I'm writing the ones there because if this was like the reciprocal, if these were flipped and you canceled everything out from the numerator, you'd have 1 over the thing. And that's a case where almost I see half, 2/3 of students not write the 1 over, not write as a fraction, but just write the thing. So I wanted to emphasize that point because I want to avoid that kind of mistake. Jack.
Can you repeat the parentheses?
Yeah. So really there's a parenthesis around each of these two things, right? The x plus 1 and the x minus 1. Now the x plus 1, it doesn't matter, the parenthesis around it, because it's positive, right? So if I distribute a positive through, neither of the signs change. The parenthesis or the negative in front of the x minus 1 means the parenthesis there definitely matters, because I need to make sure that negative applies not only to the x, but also to the minus 1. So if we didn't include that parenthesis there, we would end up with just 0 instead of 2. And you would be like, what's going on? Does that feel okay? Joe.
Can you see the restroom real quick?
Sure. Okay. Now, if we have a trigonometric identity, we can kind of add a little bit to our strategy here that's going to be a little bit more specific to a trigonometric identity. So typically we want to start with the more complicated side. For the same reasons that we kind of discussed earlier, that it's usually easier, to combine things and reduce things and make something that's big into something little. That algebraic direction of kind of moving downhill is a little bit easier than taking something simple and like building it back up and like climbing up a mountain. Okay. And specifically, when we say complicated, what we typically mean is has more terms. So like two things that are being added or subtracted is more complicated than two things that are being multiplied together. Just because that's one term. You guys okay with that? So when in doubt, convert everything to sine or sine and cosine. So if you're not sure what to do or where to start, that's an effective strategy. And the last thing is what we have to remember. We have to remember that when we're adding or subtracting fractions, we need to have a common denominator. So let's look at this next example. So our identity is tangent plus cotangent equals cosecant times secant. So which side would we want to start working on? Which one is the more complicated side? So how many terms do we have on the left-hand side? 2, right? How many terms do I have on the right-hand side? 1. So the left-hand side would be the one I'd want to start with. So multiplication is less complicated than addition and subtraction. Because really what you're doing is you're counting terms, right? So 2 things separated by addition or subtraction is more complicated than 1 thing, even if that 1 thing is 2 pieces multiplied together. Right? Like x plus x equals 2x. Right? The x plus x side is less simple than the 2x side is. It's that same kind of idea. Does that make sense? So let's start here. Now, is there anything algebraic I can do with this? No like terms to combine, nothing to factor. There's no fractions involved. What the heck should I do? Okay, to do what? Who's in doubt? Let's try to rewrite these using an identity so that they're just in terms of sines and cosines. So take a look at your identity sheet. What identity can I use to rewrite tangent so that it has only sines and cosines? If I look at my identity sheet, I see that Q1 says that tangent theta is sine theta over cosine theta. So I'm going to replace that, the tangent, with sine x over cosine x. Similarly, if I look at Q2, I see that cotangent is cosine x over sine x. Is that okay with everybody? And now you might say, well, Mr. Kulik, that looks worse, right? That's clearly more complicated. And that's okay. Things can get more complicated before they, things start coming together. But why is this now a better situation than we had before? Well, I don't have like terms per se, but I do have two fractions, right? And what can I, that are being supposed to be added together? If I want to add two fractions, what do I have to make? Common denominator. So it gives me something to do now, right, that I didn't have before. So if one fraction is cosine x and the other fraction is sine x, what is the common denominator going to be here? Very good. Cosine x times sine of x. For example, if I had the denominators 1/2, or if I had the fractions 1/2 and 1/3, and I wanted to add those together, my common denominator would be 6, right? 2 times 3, because 2 and 3 are relatively prime, right? There's nothing in common between them. Just like there's nothing in common between sine x and cosine x. They're just two different things. So the first fraction will multiply by sine x over sine x. And the second fraction will multiply by cos x over cos x. So far, so good. So when I multiply fractions, how do I do that?
You have to get a similar common denominator.
Not for multiplication. For adding and subtraction, yes.
Rob, I don't
Just
know.
straight across, right? So we just do sine times sine, which is sine squared. And we do cosine times cosine. So that's cosine squared. And we still have the plus sign. It's going to be in the middle. So that's my new numerator. Everybody cool with that? The denominator is just going to be sine times cosine. So far, so good. Now, does anybody see anything useful we can do now? There is an identity that should be jumping out at you.
Well, it's 1 over sine of x times cosine of x.
Yeah, so sine squared plus cosine squared is an identity. That's P1. So I can rewrite that just as 1. P1 says sine squared or plus cosine squared is equal to 1. I gave you guys an identity sheet last week, right? If you wanted to take that out to look at while we're doing this, that could be, I would think would be extremely helpful to look at, to have these things in front of you while we're asking like, hey, what can we do? Just saying. Not that you need to do it, but if you wanted to look at that while we're doing it, I think it would be helpful. So far, so good, everybody. So we've made quite a bit of progress, right? Now we're down to a single fraction. That's good. So we have 1 over sine x times cosine x. What do I want to do with this? Yeah. So we can think about this as like the product of two separate fractions.
Oh. And 1 over sine is cosecant, and 1 over cosine is secant.
Good. And that is what we wanted, right? So we're done.
At least with these, you know you did it right. Because it has to equal the second part.
Well, you have, hopefully, you know if you've done it right. If you made some like illegal algebra along the way to get to the right answer, like it may not be correct, but if you're doing your algebra correctly and you're like following the steps correctly, when you finish, you should get you should know when you're done. And if you can't get it, you should know that there's a mistake somewhere in the back. Usually for you guys, in my experience, it's like some algebra thing, like you've reduced something you can't reduce, or, you know, miscopied something down or whatnot, whatever. Okay. So another set of strategies that are often will be helpful. So this difference of two squares factoring pattern. This is your friend. It'll come up a fair bit. And then the other thing to do is to always remember kind of where you're trying to get to, right? You know what the answer is going to look like. Oftentimes, there's going to be some, possibly have some clues as to what you should do to kind of get to that, to get to the final answer. Okay with that? So let's look at this next example here. Which side would be the one to start, or the better side to start with? The left side. Right. So the left side, we have 1 over secant minus 1 plus 1 over secant plus 1. Typically, I like to start by looking for algebraic things to do before I start going to identities. Is there anything algebraic we can do here? Yes, what can we do with this?
There's 1 over secant minus 1 squared.
No. Well, there's nothing to reduce since the numerators are 1s, right? You can't reduce a fraction where the top or the bottom is just a 1. But I agree, there's something to do with the fractions. So what are these two fractions being, what operation is between them?
Addition.
Addition. So let's add them. What do we need to do to add two fractions? Great, a common denominator. What would that common denominator be in this case?
1.
It's not secant. So secant x is just like a variable, right? That's the way we should be thinking about this. So like if I had, let's say secant x is 3. It'd be really the same thing as trying to add 1/2 and 1/3, right? Kind of see that? What would the common denominator be if I wanted to add 1/2 and 1/3? 6. 2 times 3, right? So all I would do is multiply this denominator with that denominator, right? What should we do here? Common denominator is going to be secant x minus 1 times secant x plus 1.
So secant squared.
Well, we'll FOIL it out and see what we get. So the first fraction, we're going to multiply the top and bottom by secant x plus 1. Everybody okay with what I've written here? Okay. So we multiply the numerator together. So the first numerator, I just get secant x plus 1. Then I have the plus sign. And then my other numerator, secant x minus 1. And my denominator is secant x plus 1 times secant x minus 1. Everybody doing okay to here? Again, if the algebra doesn't make sense or you're not quite sure what happened, feel free to speak up and we can go a little bit deeper, give a little bit more explanation. I'm trying to go real slow though so I don't lose anybody behind. What else? What should we do now? Right? We've gone ahead and we added these two fractions. We made a common denominator. What can we do now that we've done that?
Can we reduce? No.
We can't reduce because
Division.
the numerator isn't being, nothing's being multiplied, it's all being added and subtracted, right? But I see a potential bunch of things that I can do algebraically. Aren't there a bunch of like terms in that numerator?
Yeah, we can add.
Let's combine some like terms in the numerator, right? So secant x plus secant x is just 2 secant x. And 1 plus negative 1 is just 0, right? So just have 2 secant x. Now how about the denominator? What do you want to do with that?
We already folded.
We have not foiled it.
Okay.
We just wrote the two products next to each other. So let's FOIL that out. Now, I'm going to observe that really what I see here is like a plus b times a minus b. That's a difference of 2 squares, so I'm going to use that multiplication pattern to shortcut through the foiling. Now, if you wanted to FOIL that out, that's certainly okay. But that's the way that I'm going to write it. Doing okay? So we're getting simpler, right? That's good. I think at this point there's nothing more algebraic to do. Can I reduce those secants? Look carefully here. You cannot. Why not? Not because one is squared, but because we have the minus 1 on the bottom. Remember the order of operations, there's like an implied parenthesis around the numerator or the denominator, so I'd have to do that subtracting 1 before I could reduce, and there's no way to kind of combine those two things. So, but that's a point, like a mistake I see students frequently make. That's why I wanted to stop and make sure that we talked about that at least. Remember, we can only reduce when there's a multiplication problem, not an addition or subtraction problem. So maybe it's identity time, right? So let's look for a useful identity here. Jay, do you see something? Yeah, so if I take P3 says secant squared is equal to tan squared plus 1. And I like that because I still have that minus 1 there that'll eat up the plus 1. So yeah, let's do that. So the numerator we're not touching. But in the denominator, we're replacing that secant squared with tan squared plus 1 from P3. So now we can combine like terms in our denominator.
That would cancel out by 1.
So the plus 1 and minus 1 cancel each other out. Now I'd like to go back and just kind of look at what we are trying to get to. So I have the 2 part of it, right? Everybody can see that? So what I would probably do here is I would start thinking about it, I think, this way, as 3 separate things multiplied together. Jay? Very good. Yeah, so let's use R6. That says that I can rewrite that 1 over tangent squared as cotangent squared. And that's good because I'm supposed to have a cotangent here in my final answer. So, but I have a cotangent squared. So what I'm probably going to do is I'm going to break that cotangent squared up. So I just have cotangent times cotangent, because now I have this whole part of my final answer. And somehow now cotangent times secant needs to turn into cosecant, right? This part here has to turn into that. So cotangent squared is cotangent times cotangent, just like x squared is x times x. Does that feel okay? And that's exactly the sort of thing, if you're not sure what I did, like speak up and make me re-explain. I'm happy to do it, or happy to repeat, or give another example, or kind of draw a little analogy. Okay. So if I go and I look at my identities, I'm concentrating on just the cotangent and secant parts. And I'm looking for an identity that relates one or both of those with cosecants, because that's what I know I need to end up with. Exactly, yeah. So J observes in Q2 that cotangent is equal to cosecant over secant. So those fellas can cancel out. And now we're at exactly where we want to be. For the record, that's not the fastest way to do this, but I think the most obvious way to do this. At least in my experience, I've been doing this a long time. This is the way that I would expect most of us to try. Mr. Kulik's a tricky jerk and would do sneaky things instead. But it probably doesn't get much better than this. At some point, you have to make a common denominator and deal with some junk. Okay. Let's look at this last example here. So I have cosine t over 1 minus sine t equals 1 plus sine t over cosine t. Which side would be the better one to work on? Yeah, it doesn't really matter, right? They're about the same. You guys kind of see that? That here there's really no bad choice. They're both, then one's not going to be any easier than the other. So for the sake of convenience, let's work on the left-hand side. I think that was I heard left and it doesn't matter, so since it doesn't matter, let's choose the left-hand side. Jay?
The right side, you could right away do the one.
So you could take the 1 and replace it with sine squared plus cosine squared, but I don't know if that's going to be terribly helpful in this case. But yes, you could do that. Right. Yeah, because you have the squareds in there. Right. So is there anything algebraic we can do? Nothing obvious, right? But there is a trick. So remember, what were the two strategies here we listed for these types of problems that we just had? One was using the difference of two squares, and the other was eye on the prize, right? So what I notice when I look at this is I go, hey, I have a 1 minus sign and a 1 plus sign. Those are like my pieces of a difference of two squares. Everybody agree with that? Now, I don't have any obvious way that I could turn cosine into a 1 plus sign. Everybody agree with that? There's no obvious thing to do with that. So how am I going to get the 1 plus sign in the numerator? Well, I'm just going to force it to be there by multiplying the top and bottom by 1 plus sine t. I can do that because I'm just multiplying by 1. And I think that's probably an excellent idea because my denominator now is a difference of two squares, which is great. Everybody kind of see that? Now, that's not obvious until you've seen this trick. So let's go ahead and write this out. Actually, let's just multiply this stuff through, right? Actually, hold on a second. Let me think. Let's think about this for a minute before I get going. So I notice here that this cosine is not there anywhere, right? Agreed? So at some point that cosine's going to have to reduce out of there. So in order for me to reduce fractions, it needs to be in a factored form. So I'm not actually going to distribute that cosine through the numerator. It's fine if you do, but you'll just end up having to factor it back off later. So I'm just going to save myself the headache of doing that by going, oh, look at that. Yeah, you can be a little bit smarter about this. Is everybody okay? Again, not the end of the world if you didn't catch that. Yes. Wouldn't be 7th hour if you didn't. Ha ha ha. Okay, I'll do my difference of two squares factoring pattern to FOIL out the denominators. We okay to how I got to here? Okay. Now I would say it's identity time. Specifically, I'm going to be looking at that 1 minus sine squared part. Do we see anything we can use on that?
Do we use P1?
I would use P1. Yeah, let's replace the 1 with cosine squared plus sine squared. And I love that because I have a minus sine squared right after it to gobble all that stuff up. Yeah. Is everybody okay with that? Oh, I lied when I said this was our last example. I guess there was one more here. But look at how great this turned out for us. Yes, sir?
Even though that one's squared, you can still like, whatever.
Reduce? Yeah, yes, exactly. So I can reduce the cosine t and the squared. Just like if I had x over x squared, I could reduce those. And that leaves me with exactly what I'm looking for. Righteous. Yes, sir.
So was all you did is you substituted the bottom, oh, the whole entire thing just went out. Oh, there we go. So you substituted the, what was it? The 1 with P1, and then when you brought it up, you just canceled out, and basically we got what we needed, kind of?
Yes, so the 1 turned into P1, as I've highlighted there in yellow.
Yeah, and then so since the signs kind of like
Canceled those up,
those
yep.
turn into 1s, but it doesn't really matter.
Oh, they turn into 0 because that's adding and subtracting.
Oh, okay.
Right?
So,
If we're multiplying and dividing and they cross out, they're
Yeah,
1s.
that's
Adding, subtracting, they cross
Which
out,
is 0.
they're 0s.
okay, so then we get the cosine squared, and then boom, boom. All right, cool.
Okay. All right. I think this is our last example now. Let me just double check before I lie to you guys again. Oh, we have one more strategy here to employ on this one. Okay. Our last strategy we have work on both sides and meet in the middle. So if I look at this problem, if I look at the left side, I look at the right side, they're both just one term, right? One is a fraction, the other is a multiplication problem, but they're still just one term. You guys see that? So it's maybe not entirely obvious which one I'd want to start with, which is why perhaps we might want to meet in the middle. Probably on my instinct would be I would start with the left-hand side because I see that I can take my cotangent squared and rewrite that as cosecant squared minus 1 using P2. Now I had to rearrange P2 a little bit to do that. But I was excited about that, doing that, because the numerator here is a difference of 2 squares, right? So I can factor that as, oops, that's supposed to be a u. So I have cosecant u minus 1 times cosecant u plus 1, and I'm digging that because I can now reduce cosecant u plus 1 and 1 plus cosecant u. It doesn't matter that they're written in different order because it's addition, and addition is commutative, right? And I'm like, all right, we're doing great here. But if I go and I'm left with just cosecant u minus 1, but I'm looking what I have left there, and it's like, oh, I don't know how to turn cosecant u minus 1 into that stuff immediately. You know what I mean? It's like maybe I simplified too far or something. So instead of starting over and trying to do something different, I'm just going to jump to the right-hand side and try simplifying that and seeing if I can end up with cosecant u minus 1. You know what I mean? So I would start here just by distributing, I think. And I like that because I have that cotangent u times tangent u. And I know that that is going to eventually cancel out to give me my 1. So the first cotangent here, I'm going to rewrite using Q2, and I'm going to use the version with the secants in it because it's being multiplied by a secant. And in the second cotangent, I'm going to rewrite that as 1 over tangent because it's being multiplied to a tangent. That leaves me with cosecant u minus 1. Very nice. So if you're getting stuck trying to get one side equal to the other, maybe you just stop where you're at and jump to the other side and try to work that to get to where you left off at. Or even somewhere along the way, right? Like if you at any point you get any two of the parts or two of the two sides equal, you're good to go. Does that make sense? And I would say that that strategy that we just looked at there could have been particularly helpful on this problem here. I think that this turning into that would have been quite easy rather than doing what we did. Taking 2 cotangent times cosecant. Oops. Probably would have been pretty easy to turn that into secant over tangent squared. But either way, no big deal. It wasn't too hard doing it what we did. All right. So that's that. That's it. That's the idea for 5.2. That's all the chapter 5 we're going to do this year. That's pretty cool. So the remainder of your stuff for chapter 5 on your problem set is going to be these identities 47 to 62. And then working on the review for the chapter 5 test. I just want to point out to you the format here for the chapter 5 test because it's a little bit different than some of these that we've had in the past. So you have 8 questions total. Only 7 of them you have to answer. There's going to be 2 required questions at the beginning of the test that are simplification problems, similar to what you did on the first 20 problems on the review. And then you're going to have 6 identity proofs. You can choose to do any 5 of those. Okay with that? So you have a little bit of choice there. You don't have to do all of them. Those are going to come exactly from questions on the review. So the review, there's 21 through 62 on the review, are all identity proofs. 5 of those are going to, or all 6, or the 6 questions on your test are going to come from that set. And you can pick to do whichever 5 you want to do. They're not going to be ordered in difficulty. They're typically going to require 2 to 4 steps if solved efficiently. But there might be proofs that will require more work. They're all worth the same amount of, all the proofs are worth the same amount, so pick the ones that look easiest. I'm going to grade the first 5 that I see marked to grade, or that are left, like not marked blank, that are not indicated to, to grade or not grade. So I'll have a little box on there that says grade this or don't grade this. So the first 5 that I see that aren't marked don't grade, I'm grading. So make sure that you're being careful on the test or whatever. And if you change your mind, you can always go back and like put an X through something and like change it to don't grade. You don't have to erase anything. Yeah. So that's going to be the last of our stuff. So the rest of today, you guys can take to get started on that stuff, and then Wednesday and Friday are going to just be days to work on stuff in class. And then we'll take the Chapter 5 test on, well, this is the B day, so Tuesday next week. We'll do Chapter 6 in one day because it's what I'm going to ask for you guys to do. It's basically a new set of identities, but we're just going to do some numeric stuff with them. So we're just going to be using the unit circle and some new identities to kind of fill in some, to fill in some formulas to get some exact answers for things. Which I think is a one-day lecture. And then start the exam review or the test retake if you're opting to do that, which again is optional. You could just take the double high test score if you're happy, or if that feels like it makes more sense to you or whatever. Okay. Cool.